Okay, welcome back. A few things before I get started. There will be one more problem set, but it will be due the last day of class, Monday, a week from today. And toward that end, I'll pull my office hours into the morning on that Monday also. What else? Oh, the video for last Monday, I've posted it now. I wasn't able to post it after class, and anyway, travel issues. Any questions or issues on the class at this point? I realized a number of you have asked me about the course evaluation. There's a deal where I drop your lowest problem set score if you complete the course evaluation when it's open. It's run not by me, it's completely run by the university. And you guys get, I believe, get emailed when they become open. Are they open at this point? Not yet. Okay, but it's sometime really soon, and it closes before the final. And I'm not sure how much before the final. I'll try to remind you at least once during class, once it's open, to go after it. But keep an eye out for it. If you complete it, I'll drop your lowest problem set score, even if it's a 0. Okay, so it's worth doing it for most of you, unless you've gotten consistently perfect scores, whatever. I guess that, anything else? Things I've forgotten? The final's the 14th, which is, I believe, is a Thursday in the morning. It's a 60-question multiple choice exam, so it's twice as big as a normal midterm. And I consider it as, I think of it as 50% the third midterm. That is material since the second midterm. And the other 50% of the exam is open season the whole semester. All right? Questions, same style you've seen before. All right, with that then, I'll start talking about clocks. So I finished then the story of heat and playing with heat, moving it around, either by letting it flow naturally or manipulating it. And now we'll go into something different, but not altogether new. We've seen these things before. Clocks, just to foreshadow things, clocks by and large are built around rhythmic motions of the type that we've already seen. You bouncing on a bungee cord in problem set 3, I think it was, off Ruffner Bridge. Person at the end of a diving board bouncing up and down. Flagpole waving back and forth. Pendulum swinging back and forth. Clocks are built around exactly those same rhythmic motions. And so this is sort of a time to go somewhat in-depth into those rhythmic motions. And then once I get done with clocks, we'll look at musical instruments, which are built around the same rhythmic motions. And probably, we might or might not get into talking about waves, which again are built around those same rhythmic motions. And so this is the same story over and over in more elaborate contexts. All right, so the first question is, you're bouncing up and down gently at the end of a diving board, springboard, never leaving the board surface, so you never become airborne. You're always in contact. If you bounce up and down a little further, here's you sitting on the end. I don't know, I can put something there. And you're bouncing up and down. You're not coming off the surface. And if you bounce a little, it takes you a certain amount of time to complete each bounce. And if you bounce more, it takes you a certain amount of time to complete each bounce. And the question is, if you bounce the bigger bounce, does it take you, how does that time it takes you to complete a full bounce, up, down, back to where you started from? How does it compare to back to when you were bouncing a little? So does it take longer time, increase? Does it take shorter time, decrease, or the same time? You okay with the question? How many think that it will take longer to complete the bounce when you bounce up and down farther? That's A. Okay, how many think that it'll take shorter to complete the bounce if you bounce up and down farther? That's B. How about the same time? Okay, so the vast majority actually are going for the same time. And that, it turns out to, okay, I'll give away the answer. That's the right answer. It actually does take the same time. It's a remarkable thing because you are traveling farther. And if you're simply traveling farther and nothing else changes, it's going to take you longer to complete it because your velocities are all going to be back what they were, and it takes you longer to travel bigger distances. On the other hand, when you bounce up and down farther, you get you experience stronger pushes back towards where the center, the equilibrium. And if the stronger pushes were the only thing that happened, then you would simply move through your motions faster because you would accelerate faster in response to stronger forces. And it turns out these perfectly cancel. The fact that when you do a bigger bounce, you have farther to go, but the forces are all bigger. And the bigger forces create bigger accelerations. And it drives you through the motion in the same amount of time. So yes, you go farther, but you go faster. It all cancels out perfectly. Okay? So that doesn't always happen. There are systems that go through rhythmic motions that have weird, the distance you travel does matter. The bigger motions have a different time involved than the smaller motions. But there's a whole class of rhythmic systems in which the time it takes to go through the rhythmic motion doesn't depend on how big that rhythmic motion is. And that class of systems that do this are known as harmonic oscillators. So this is the story of harmonic oscillators, which are, I mean, for physicists, they're the centerpiece of so much of physics is built around harmonic oscillators. I won't wax on any more poetic. It's a central feature of our physical universe. Okay, so some observations about clocks. They divide time into uniform intervals. I imagine when people were first trying to figure out how to think about time, they had other ways of imagining its passage, of course, across a day or a month or a year. We now divide time into uniform pieces, seconds, hours, years, and so on. We measure time by counting the passage of those intervals. So 1 second, 2 seconds, 3 seconds, 4. It's about, I'm going a little fast. 1 potato, 2 potato, 3, or 1 banana, 2 banana. Hopefully you have some trick for counting seconds approximately right. Some clocks use motion to mark their intervals. So you're actually seeing something going through its motion, and a hand of a clock may actually advance to point at different seconds and different minutes and different hours going by. Some clocks appear to have no motion involved at all. Most electronic clocks, and I mean, we're in an odd technological period where probably a lot of you don't have watches anymore. I still wear a watch because I'm going to use it, all the little gadgets on it, timers and stuff. But for those of you who do have a watch, the cell phone's it's different. The cell phone actually has lots of clocks in it, but they're not necessarily involved in displaying the fact that it is now 1:07 p.m. But all traditional clocks that are around, they're built around these rhythmic motions. And even the ones that don't appear to have anything moving, there's something moving in them. Your cell phone has at least one crystal oscillator, a quartz crystal oscillator. I mean, it probably has more than one. And there's actually motion in that thing, even though, so an electronic watch of the type that I'm wearing, and you might or might not have one anymore, it's actually got something moving inside all the time. They require energy to operate, and that's an inevitable consequence of the law of entropy. That you just can't keep things going without creating disorder. As time goes on, you create more and more disorder. Watches are no different. They cannot manage to keep everything under control, and so they create disorder. In order to keep them functioning well, you have to keep bringing in new energy and new order to keep them going. And lastly, clocks are good but not perfect. And as the years have gone by, people have built better and better and better clocks, but there are sort of fundamental limits to how good any particular clock can be. Certainly there are realistic reasons why any clock can't be perfect, but there are even theoretical reasons. Okay, so that's the background on clocks. And so the questions I'll go after trying to tease out the physics of clocks, and in large part about the harmonic oscillators, is these 4 questions. And the first of which is why don't any modern clocks use hourglasses, which is simply a way of going into the idea that we use these rhythmic motions because they're the only really reliable way of keeping track of time in a predictable, controllable manner. Yeah, an hourglass can measure time reasonably well. They used to have little egg timers that were just for soft-boiled or hard-boiled egg. You flip the little sand hourglass upside down, and I don't know whether you remember the Wicked Witch of the West flipping over the, this is all the time you have left. In any case, they're good for measuring a single interval, and they're pretty accurate. But if you want to keep on ticking off the intervals, one after the next, you're either going to have a lot of employees to be there flipping the hourglasses, or you're not going to get a very accurate clock. So the clocks that we currently use are all built on self-repeating motions. There's nobody involved in flipping over the hourglass to get the sand going a second time. It's built into the physics of the clock's timekeeping mechanism. So I'm going to talk about timekeepers. The timekeeper is sort of the heartbeat of the clock. The clock really finally, I can sort of jump ahead. The clock is going to distill down into 3 pieces. It's going to have a timekeeper, which is the rhythmic the pulsar, the ticking off the time in uniform intervals, approximately the way your heart does, unless something excites you one way or the other or something. Time runs fast. Second part, a source of energy, because the timekeepers inevitably waste some of their energy of motion, the energy that's equivalent to work. They turn it into thermal energy, and they stop doing their motion. To keep them going, you have to keep resupplying the energy. So there's going to be a source of energy. And the third thing that goes into a clock is a system for counting the intervals. How many times has the timekeeper ticked? And that's really all there is to most clocks. That's certainly all there is to this clock. I mean, I'll just jump ahead here. This is a pendulum clock, and it's a pendulum clock that you can just buy as the works to put in your own beautifully woodworked cabinet, which I never built. So here it is. Here's the clock. The timekeeper is a pendulum, which swings back and forth, but right now it has no energy to swing back and forth, so I have to put the energy in. How do I do that? I do work. I'm going to lift, there's a weight down there, and I'm going to lift the weight up on its chain. So I'm doing work. I'm pulling down as I'm moving the chain down. It in turn is doing work on the weight, lifted it up. The weight's now packed full of gravitational potential energy. That's the energy source for this clock, that descending weight. The timekeeper is that pendulum. Oops, swing straight. The pendulum is now ticking back and forth, and it is the timekeeper. It's the source of a nice steady rhythm. And the last part is the counting mechanism. That counts how many times that pendulum has ticked. And the counting mechanism is a bunch of gears up here and 2 hands, a minute hand and an hour hand. And that's all those minute hands and hour hands are. They're just counters. They're counting how many times the pendulum has swung back and forth. And the pendulum is given a little push each time it swings by the descending weight. It takes about a week for this weight to go from the height it's at currently to the floor. That's about a week. And during that time, the energy released by that descending pendulum will have gone into the pendulum to keep it swinging against things like air resistance and friction and whatnot. And the hands will have gone around, the hour hand will have gone around 14 times for 7 days of passage. That's about all there is to it. Does that make sense? You okay with that? If you've gone to visit Monticello, which surely a whole bunch of you have done, there's Jefferson's clock up there by the entry, and the energy source is a bunch of like cannonballs on a cable. And actually last semester, or last year, I had somebody who was the person who had to wind it, was in this class. Maybe at least for a summer, maybe for during a year. And it was hard work getting those cannonballs back up. But they descend down from a certain height at the beginning of the week. They actually go for 7 days, and they descend into the basement. as they're giving up the energy that's necessary to keep that clock going. Hopefully this is familiar to many of you who've done those tours and stuff. Okay? Any questions? I mean, I haven't given you any details yet except for the basic concept. So modern clocks use these rhythmic motions because they're the only way of getting a reliable, reproducible measure of the passage of time. Single intervals, yeah, fine, but multiple intervals, no. About repetitive motions in general, they all involve a system. Well, they all involve. The vast majority of repetitive motions are built around a system that has a stable equilibrium. So it has some situation which it can be have zero net force. It could sit there all day, like this stick. This stick has a stable equilibrium right there. Zero net force, it's at rest, it stays at rest. And it's a stable equilibrium, I'll remind you of that one, meaning that if you take it away from equilibrium, however you want to do it, it experiences restoring effects, restoring forces, restoring torque, something. It spontaneously pushes itself back towards the equilibrium. Not away, which would make it an unstable equilibrium, but back toward it. Therefore, it's a stable equilibrium. So this stick has that, a ball in a bowl, rolling back and forth. It wants to be at the bottom. This pendulum has a stable equilibrium. It's at it right now. At this point, zero net force, meaning it's inertial here, so if it's at rest, it stays at rest. If we're moving, it would be inertial right through that stable equilibrium. And it's stable because anytime I take it away from equilibrium, it experiences forces that push it back towards the equilibrium. Okay? So you can have lots of systems that have these stable equilibria, and they will move around. Ding. Got behind. I had to, anyway. Random thoughts go through my head, no particular value. Most of the time, that's the case. What do I want to say? Yeah, repetitive motions will occur around the stable equilibrium until you run out of excess energy. They're all kept in motion by excess energy, something we dealt with on the bungee jumping situation, for example. When you bounce up and down on the bungee cord until you run out of extra energy. Or the car, remember the car driving along, hitting a curb, and suddenly having the springs compressed, and then the car bounces up and down for a while, as a harmonic oscillator turns out, until you waste the energy with a shock absorber. So they all will do this. You can use that repetitive motion, this repetitive motion around a stable equilibrium, as the timekeeper for a clock, assuming, of course, that the repetitive motion has a very nicely defined time, that it takes, for example, 1 second to go through its motion, and that it's really picky about that. Well, the time that it takes to go through that repetitive motion shouldn't depend on very much if you want an accurate clock. It shouldn't depend on the last election. It shouldn't depend on how much energy is stored in the clock, whether it's recently been wound or whether it's almost out of energy, where the cannonballs are in Jefferson's clock. It shouldn't depend on temperature or air pressure, other external influences, and it shouldn't depend on the act of counting the number of pulses, of beats of the timekeeper. So in part, the clock's got to be very careful not to mess up the counting process, not to mess up the rhythmic motion with the counting process. I mean, just for example, you can count time. This takes about 4.5 seconds, last I remember, for this guy to swing back and forth. And you can go tick, little 1, 2, you can do that. But you don't really want to go like 1, okay. 2, you can, if you're too harsh with the poor timekeeper, you can make it move, you can lose count. It won't keep a steady beat. Okay, last tidbit here is with these timekeepers, these rhythmic motions, and so I've given you said very little that's sort of about physics, more about just general observations. You want the rhythmic motion, the time it takes to go through that rhythmic motion, not to depend on how big the rhythmic motion is. Why is that? Because it turns out it's very hard to control how far a rhythmic motion occurs over. So for example, this thing keeps a steady beat about 4.5 seconds to complete its round trip motion. And you can count the time it takes to complete the motion with exquisite accuracy. You can come in here, we could put instruments around this, and we would exactly count how long it took to go through its motion. And if we counted this motion for a week or a month, we would get a very specific number of swings that have gone by, and we have a really good idea of the time involved. But it's a lot harder to know how far the motion is and control that motion to better than maybe a part in 100. If the time it took for this thing to swing back and forth, we're very sensitive on how far it swung, we'd have to be here very carefully saying, has it come to this point? It should stop right there. Oh, wait, didn't go far enough. It's not keeping accurate time. Long and short of it is clocks don't want to be dependent on how big the swing is. This pendulum clock here, depending on when I got it, how I started it, it's swinging just a little bit right now, right? You want it to keep the same beat, even if I make it swing farther. And I don't know whether you can see it, but it's pretty much keeping the same beat. It's swinging about twice as far as it was a minute ago. And it will settle back down to approximately where it was. But you don't have a lot of control over how far it swings, bottom line. And so you don't want the timekeeper to be very dependent on how far it swings. Is that okay with everybody? I don't want to dwell on it forever. I'll stop with that. And that brings us to a specific class of oscillators that have a time over and back that doesn't depend on how big the swing is. Okay, so to keep talking about this, I want to develop a few words, physics language, a few more physical quantities, things to specify what's going on here. The first is the period of a rhythmic motion. And period is the time it takes to complete one full cycle of a rhythmic motion. What was that? I don't know. Random attack here. The period of this pendulum, I told you already, is 4.5 seconds. It's the time between now and its return to that same situation, now. Okay, so that's just called the period of an oscillating or vibrating or rhythmic system, period. Okay? Frequency is the reciprocal of period. So period is how long it takes to complete a motion in seconds. Frequency is how many motions the system goes through per second. It's 1 over period. So the units are flipped. The units of period are seconds. The unit of frequency are per second. 1 over second. It's rare that we would talk about the frequency of that bowling ball pendulum because it's very low frequency. It completes something like 2 and a little bit. Well, no, it takes 4.5 seconds to complete a cycle. That means its frequency is about 0.2 cycles per second, a little more, 2.3 or something, 0.23 cycles per second. But there are systems that go a lot faster, and talking about their period, the amount of time it takes for them to go through their cycle becomes awkward because that time becomes very short. So instead, we flip things over. We take 1 over period. We talk about frequency, and then it's the number of cycles per second, and that becomes a more reasonable number to talk about. So I can probably go through the whole sequence with this stick. This, incidentally, is a harmonic oscillator. It fulfills all the requirements. It has an equilibrium. It's a stable equilibrium. And we'll see that it has all the features of being a harmonic oscillator, and it has the behavior of having a period that doesn't depend on how big the motion is. But what I want to do with this is I want to go from the world of talking about a period That's about 1 per, I'm going for 1 per second. That's about 1 per second. So the period is 1 second up and down. Pretty close. All right? It happens also, if the period is 1 second, then the frequency is 1 cycle of motion per second. Is that okay? Period is the time. Frequency is the number per time. If I shorten this stick, I can go even slower just because I can. This has got a period probably over a second, and therefore frequency is less than 1 per second. If I shorten the stick, though, it's going faster. So the period's going down to a third of a second, or half a second, third of a second. That means the frequency is 3 cycles per second. Is that okay? And if we go higher still, now talking about the period, it's pretty fast, 1/10 of a second. Well, that's not that fast. About a 1/6 of a second. So its frequency is about 6 per second. If I go further, it's going faster. Its period's quite short now. A 1/10 or a 15th of a second, it's more like 15 cycles per second. If I get it shorter, what I want to do is I want to carry over. Can you hear it? It's now developing a pitch. It's a tone. The point being that as the period gets shorter and shorter and shorter to the point where we stop even talking about it as a period because it's a too tiny fraction of a second to worry about. And we flip things over and we talk about frequency instead, how many cycles it completes in 1 second. As that enters a certain range, it enters the audio portion of the sound spectrum that we hear. And we can begin to hear these rhythmic motions because of their influence on the air, and ultimately then on our ears. And we hear things in the frequency range between about 20 cycles per second and about 10 or 20,000 cycles per second. Those are the frequencies I'm talking to you right now with a lot of sound that's mostly in the 200 or 300 cycles per second range, that being sort of the area of my voice. People with higher pitched voices, it's going to be more cycles per second. Is that okay? One tidbit about frequency is the unit of period is simply seconds. The unit of frequency is per seconds. Or sometimes we will put the word cycle per second just to sort of specify what is it per second. It's a cycle. It's a complete cycle of motion. And the unit, the cycle per second, or the per second, has its own name, which I may use from time to time. It's called the hertz, H-E-R-T-Z. And so this is 128 hertz. Not that high-pitched thing. That one. That's 128 cycles per second. Okay? $128 hertz. Amplitude. Next tidbit of or physical quantity. The amplitude is the extent of the motion from one end to the other. And actually, it's typically measured from equilibrium to the extreme extent. So in this case, equilibrium's here. That's the amplitude. It's about a little over 3 feet or 1 meter. This is about a 1 meter amplitude of motion. Is that okay? In this case, the amplitude of motion maybe 1 centimeter. Now that's 10 centimeters. Now it's back to 1 centimeter. Is that okay? Last thing, the Timekeeper. I've already talked about Timekeeper here. It is this rhythmic system that beats off time in a reliable way. And so perking right along, the period, or equivalently the frequency, of a good timekeeper shouldn't depend on the amplitude of motion. So that's where I've been heading and meandering through. You don't want the timekeeper to be sensitive to how big the motion is. If it keeps a steady beat, regardless of the size of its motion, it's going to be a good timekeeper. It has a shot at being a really good timekeeper. And so that's what we're looking for. Are there such rhythmic systems? And it turns out, yes, there's an entire class of them. All of them are, well, the whole class is called the Harmonic Oscillators. And they have a few specific requirements. First off, to be a harmonic oscillator, the system has to have a stable equilibrium. Not so surprising. The second requirement, and pretty much the last one of a harmonic oscillator, is that its period of motion, no, we're not there yet. That's cause and effect. The cause. The requirement is that the restoring forces it experiences, or whatever restoring influences, whether they're torques or forces, they have to be proportional to how far you take the system away from equilibrium. And proportionality is a very specific requirement. It says that there is a linear relationship between how far you take it away from equilibrium and how much restoring influence shows up. So this stick, and I've been claiming it fits the bill already. It is a harmonic oscillator. I can adjust it, so I have to clamp. The adjustment is all making it longer and shorter, and therefore more massive, less massive, in part, and also stiffer. And this is stiffer. This is less stiff. This is stiff. Okay, but I have to clamp it well here, and I'm being careless. But if I buy in and clamp tightly here, and now that really is the equilibrium right there. And if I take it away from equilibrium with my hand and I shove it down 1 centimeter, it experiences a restoring force of, let's just say, 1 unit. I don't know how, it's some amount. If I push it down 2 centimeters, it experiences 2 units of restoring force, twice as much as before. 3 units down of 3 centimeters down of distortion, it experiences 3 units of force. Basically, the restoring force is proportional to how far I take it away. Where proportionality, hopefully you have a good sense for, proportionality is really this linear relationship, this one-to-one relationship between displacement and force. Is that okay? If you satisfy those 2 requirements, stable equilibrium and restoring influence that's proportional to displacement, bang, you've got a harmonic oscillator. That does it. And the symptom of a harmonic oscillator, the outcome, what you get for your struggles to have a harmonic oscillator is you get a system that goes through its rhythmic motion with a period that doesn't depend on amplitude. If you take it a little bit away from equilibrium and let go, it bounces up and down at a certain rate. So you can either think of it in terms of a period that it takes to complete a cycle, or the number of cycles the frequency, the number of cycles it completes per second. If you take it a little bit away from equilibrium and let go, you get a certain period or a certain frequency, same equivalent. If you take it farther away from equilibrium and let go, you get the same period, the same frequency. That's the whole point. It doesn't matter how far you take it away. Okay? The same thing happens here. If I take, this is equilibrium here. If I take it just the barest little bit away from equilibrium, it takes 4.5 seconds to go over and back. I've done this in past years when I'm sitting here counting. Doing 1 cycle isn't enough. You have to do several. It's very tedious, so we'll leave it. That's 4.5 seconds over and back, give or take. If I do the big sweep here, it's still 4.5 seconds. This is another harmonic oscillator. It's not quite perfect. If you calculate up the restoring forces that it experiences, they're very close to being proportional to how far you take it away from equilibrium, but not quite. And that not quite becomes worse as you go farther and farther until finally, if you take it like horizontal relative to the connection up there, it's rotten. But as long as you stay pretty close to center, it's almost a perfect harmonic oscillator, meaning the restoring force is almost perfectly proportional to how far you take it away from equilibrium. Is that okay? So this guy ticks off time beautifully, whether you swing it a little or a lot. Same tick. And that is why pendulum clocks were sort of the classic standard timekeeper. They were the standard clocks. The pendulum was the standard timekeeper in so many non-portable clocks. It still is. All right? It's a harmonic oscillator. As long as you set it up right, it ticks off time very steadily with a period that's independent of the amplitude of the swing. So about harmonic oscillators is another way to look at their behavior is they have an inertial aspect, which in this case really literally is a mass. So that bowling ball wants to keep doing what it was doing. So it has a tendency to go in a straight and true constant velocity. And it also then has a spring-like restoring force aspect. So what's a spring? If you remember Hooke's law from way back, when I was talking about spring scales, what Hooke's law observes is that many objects, when distorted away from equilibrium, from their equilibrium shape, develop a restoring force that's proportional to how far you've taken away from equilibrium. That's the behavior of a theoretical spring, and it's realized pretty nicely by a spring. It has a restoring force that's proportional to displacement. So it's kind of a battle between the inertial part wanting to keep doing what it was doing and the spring saying, no, 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 I want you back at equilibrium. So the inertial part goes through equilibrium, and the spring is now totally happy, but the inertial part is inertial and coasts. It goes right on through equilibrium. It goes out the other side, and the spring begins to say, no, 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 come back, come back. And the inertial part finally is persuaded by the spring to slow to a stop and come back. And then it coasts right through the spring's equilibrium. It's clear in my mind, but I'm not sure I'm conveying it very well. Let me show you this mass bouncing on a spring. So here's the spring, and the presence of gravity in the story, bizarrely enough, doesn't matter. What gravity's influence on this mass hanging from a spring is only to shift the equilibrium downward from about here where it might be without gravity to there where it is with gravity. Once that shift has occurred, gravity's influence is nothing. So you can think of this as just a battle between the spring wanting the mass back there and the mass just wanting to keep doing whatever it was doing. So if I take the mass away from center and let go, the mass keeps trying to go at a steady pace in a straight line, and the spring keeps fighting to get it to go back to equilibrium, and that causes the mass to keep going to one end and turning around, going to the other end and turning around, back and forth, coasting through equilibrium over and over and over. And this battle takes the same amount of time for a cycle, whether I bounce it a little bit. Oops, let me take, where's a little bit? There's a little bounce. Little bounce. Now the disagreement is mild. The spring is never taken very far away from its favorite shape, and the mass is never going very fast. So the two are content to bounce back and forth about their equilibrium with, it's about once per second. 1/1000, 2, about once per second. And if I make it bounce a lot, it's still 1,000, 2/1000, 3/1000, 4. It's about the same time. And in principle, it should be exactly the same time. If it's a perfect spring, perfect mass, which it's hard to be not a perfect mass, the period's exactly independent of amplitude. Okay? What else do I want to say with this? The period depends on, however, okay, for this given mass on this given spring, the period does depend on the amount of mass the mass has and how stiff the spring is. The stiffer the spring is, the harder it shoves the mass back towards equilibrium, so the faster everything happens. So if I stiffen the spring, I'll take this spring out. I believe this is a stiffer spring here. Same mass, stiffer spring. This spring now cares more, and this bounces faster. Okay? It's just the spring is pushing harder, go back, go back, go back, and drives it through its motion faster. So the period of a harmonic oscillator gets faster as the spring gets stiffer. You have a feel for what stiffer means? That it fights harder for any distortion. Take it 1 centimeter away from its favorite shape, it pushes harder. On the other hand, if you boost the inertia by using a mass that's got more mass, that will slow everything down, because now the spring has more trouble getting the attention of this mass and changing its motion. So that's slower again. Okay? So in any harmonic oscillator, there's going to be an inertial part, and there's going to be a spring-like restoring force part. And as you increase the inertial part, like more mass, you slow things down. And as you stiffen the spring-like part, you speed things up. And so you're choosing a battle between these two parts. And you sort of can intuitively predict whether something's going to be faster or slower. So I can leave that there, but think about, like, how would you stiffen the restoring force part of a pendulum? So the pendulum really does have, it's actually an odd one for mass. Let me not worry about that for a second. But if you want to stiffen the spring-like part, how would you do that? Well, the way you can do that is make the pendulum shorter. If you make the restoring force comes about because as you pull the pendulum away from center, it goes up. You're lifting it. And it's kind of trying to roll down a invisible ramp of varying steepness to get back to center. It wants to be at the bottom of the ramps. If you shorten the pendulum's string, you make it get steep faster. So here's a pendulum now that's considerably shorter than the bowling ball one. And instead of taking 4.5 seconds to complete its swing, this is about a 2-second over and back. Is that okay? This guy, being shorter still, mass is the same. Mass is a messy thing with a pendulum, but I'll come back to that. This is a stiffer spring still. The spring-like part's stiffer. The restoring force is stiffer. And this is even stiffer. This guy's about 1 second over and back. This guy's about, I don't know what it is, 1.5 seconds. This guy's about a 2-second. Is that okay? It turns out that for a pendulum, its period, how do I want to do this? Let me show you first an awkward detail about pendulums. I've shown you that a mass on a spring, it's very simple. The mass is the mass. That's the entire inertial part of the story. The spring is the spring. That's the entire spring-like restoring force part of the story. It's a battle between the two of them. If you increase the mass, you slow things down. If you stiffen the spring, you speed things up. Okay? Pendulum. Pendulum's a little peculiar. A pendulum, the mass involved is the mass of the pendulum bob. That's the thing that's going through the motion. But the restoring force, where's the restoring force? The force that this thing experiences is related to the weight of the bowling ball. It's a piece of the weight. The restoring force comes about because when the bowling ball is taken away from center, it's as though it's riding up a ramp. This is the ramp. But the ramp gets steeper as you go farther away from center. The ramp is getting steeper. So the ramp is steep here, and then it goes down, and then now it's going up that ramp. Now it's going. Okay? So the force is a ramp force. It's a little, and the ramp force gets stronger as you get farther from center because the ramp gets steeper as you get farther from center. But if you remember the ramp force, it's a fraction of the object's weight. It's related to gravity, how strong gravity is. The restoring force, therefore, on this ball is proportional to how far I've taken away from equilibrium, and it's related to how long the string is, because the longer the string is, the farther I have to take it away from center before the ramp gets steep. And lastly, it's related to the strength of gravity and the weight of the ball. Where's this all going? The restoring force on this ball is also related to the ball's weight. Mass. The ball's mass. What's the point of this? The point is, I can't separate the pendulum cleanly into a mass, where the inertial part is strictly the mass, and a restoring force part that has nothing to do with the mass. In the case of the bouncing object on the spring, the restoring force had nothing to do with the mass that was hanging here. The restoring force was realized only by the spring itself. It's a feature of the spring, not of the mass. This is not going as well as I would like. Let me do this again over here. This guy's restoring force also depends on the ball's mass. The more massive the ball is, the stronger the force is that pushes it back towards center, because it's a weight force. It's a weight-related force. So if I increase the mass of the bowling ball, unlike the bouncing mass on the spring, where it slowed down, if I increase the mass of the bowling ball, yeah, it's got more inertia, but it's also got a stronger restoring force. And that cancels the increase in mass. So if you hang on the ball, the wrecking ball, a little bit of modern popular culture, or maybe a couple years old, if you hang all over the bowling ball, its period doesn't change. Why not? Because yes, you add mass to the ball, but you also add weight to the ball, and that stiffens the restoring force. It pushes back harder towards center. Is that followable? So the point then is, the pendulum is a very unusual harmonic oscillator where you cannot slow it down by increasing the mass of the inertial part, because when you do that, you strengthen the restoring force as well. So the time it takes for this guy to go through its motion depends on two quantities. It depends on the length of the string. The longer the string is, the weaker the restoring force gets, because taking it away from center, you have to take it away from center a long distance before a large restoring force shows up. This one, I'm getting a large restoring force now, but I'm many feet away from center. Whereas if I take the little pendulum over here, if I take it only a few inches away from equilibrium, a large restoring force, a correspondingly large restoring force shows up. So the length of the string slows the pendulum down. The longer, the slower. And the other thing that affects the pendulum's period is the strength of gravity. The stronger gravity is, the stronger the restoring force is, the stiffer the spring-like effect is, and the faster the period becomes. So if you lengthen a pendulum, leaving everything else unchanged, you slow it down. If you strengthen gravity, leaving everything else unchanged, you speed the pendulum up. And if you change the mass of the pendulum bob itself, it has no effect because of this cancellation. So let me just give you a few observations about pendulum clocks then based on this. They are harmonic oscillators. As long as they swing the pendulum not too far, which they don't, they follow the rules. They keep a gentle swing, but they don't have to control it super carefully because it's a harmonic oscillator. As long as you do that, you've got a clock, and the timekeeper for a pendulum clock at about a quarter of a meter long, which is about 8 inches, a little over, about 8-9 inches. That's a 1 second pendulum, meaning that it swings over and back, returns to its original place every second. in order to make a 2-second pendulum, you have to quadruple the length, because it turns out that the period of a pendulum is proportional to the square root. I can't help it. It's a square root of the length over the strength of gravity. So if you want to get a 2-second pendulum, you go to about a 1 meter, just under a 1 meter pendulum. So grandfather clocks frequently will have a 1 meter pendulum, which ticks off 2-second intervals. Tick, tick. And wall clocks, pendulum wall clocks, being more compact, have a 1/4 meter pendulum, which ticks off seconds. And they have to avoid air resistance, so they go, instead of using a pendulum bob, they flatten it into a disc, which slices better through the air for reasons we've already encountered with aerodynamics. Okay, well I'll put last tidbits on pendulum clocks and then talk about other kinds of harmonic oscillator clocks on Wednesday.